For Chapter 3, we'll be looking at atmospheric temperatures. In Part 1, we'll look at seasons, solar declination, annual temperature ranges around the globe, daytime heating effects, nighttime cooling effects, and the diurnal temperature range, the difference between daytime highs and nighttime lows. The seasons are caused by Earth's tilt with respect to its orbital plane. The area with the sun most directly overhead, known as the solar declination, gets the maximum solar flux at the top of the atmosphere at solar noon. Here we can see, due to the Earth being tilted and swinging around the sun once per year, there's a period where the sun's southern hemisphere has perpendicular light coming in, and that's the winter solstice. There's a period where the northern hemisphere is tilted towards the sun, and that's summer solstice. And there's two times during the autumnal equinox around the 22nd of September and the vernal equinox around the 21st of March, where the sun's most directly overhead at solar noon, exactly at the equator. Here we're looking at perpendicular rays coming into the equator, which we know is the maximum solar intensity you'll get if it comes in normal to the surface, and more oblique rays coming in at 60 degrees north latitude here, which will be spread out over a greater surface area, thus reducing the intensity. These graphs are showing that the solar declination again shifts from 23.5 degrees north during the summer solstice, coming in perpendicular at 23.5 north, and then it shifts to 23.5 south during the winter solstice, and then during the equinoxes it's coming in perpendicular exactly at the equator. During the equinox periods, this is the only time where all latitudes have 12 hours of day and 12 hours of night. This graph is showing the solar declination in degrees versus Julian day number. So starting down the lower left, in the winter solstice, it's at 23.5 degrees south, crosses the equator during the vernal equinox, heads up to the north at 23.5 degrees north during the summer solstice, and then crosses the equator again during the autumnal equinox. Now the blue line is showing that solar declination versus day number, whereas the red line is the derivative of that, looking at the change in solar declination per week, looking at how many degrees change happen per week. You can clearly show with the blue line that it's changing quickly, and that's what expressed by a positive value here, where the solar declination is heading north very quickly. As it crosses the equator, that is when the solar declination is changing most rapidly, which means that as it comes up here to 23.5 degrees north, it's spending a whole lot of time at those latitudes. What this means is that the sun is directly overhead at solar noon for 70 to 80 consecutive days at near 23.5 degrees north and near 23.5 degrees south. This helps make the world's hottest temperatures occur in these locations since there's an accumulation of heat. This widget here can get us thinking about the number of daylight hours and how that changes at different areas across the globe. The first thing to consider is that at the equator, the number of daylight hours does not change over the entire year. It's exactly 12 hours of daylight and 12 hours of nighttime. However, as we head north here, we're starting to see a shift. It'll take us up to about 30 degrees north, and we see now that at the summer solstice it's 14 hours of daylight versus 10 hours of nighttime, and in the winter solstice it's just the reverse, just 10 hours of daylight. As we head further and further north, getting to about Boulder's location, 40 degrees, we now see that our summer days in around June 21st are 15 hours long of sunlight, leaving us just 9 hours of nighttime. And the reverse is true during our winter solstice. So as we go further and further, this effect becomes even more pronounced until finally, if we get north of the Arctic Circle at 66.5 degrees, we'll find that there's a period of time where the sun never goes below the horizon and you have 24 hours of daylight for a certain period. So in summary, large variations in the length of day are observed as one moves poleward. The change in the length of the daylight period strengthens seasonal variations in temperatures that were originally caused by changes in the solar elevation angle, or the solar intensity. Here we're looking at just some geometry. The zenith angle is the angle at which the sun is from directly overhead. For instance, if the sun's directly overhead, the zenith angle is 0 degrees. If the sun's tilted 30 degrees down towards the horizon away from directly overhead, the zenith angle is 30 degrees. The elevation angle is just the opposite. They're measuring off the horizon line and going upwards. So if the sun's 25 degrees off the horizon upwards, that's a 25-degree elevation angle. Azimuth angle is just the compass measurement measured clockwise from north, with 90 degrees equals east, 180 degrees south, 270 west, and 0 degrees or 360 degrees north. If one needs to find the solar elevation angle and they're given the zenith angle, it's just 90 degrees minus the zenith angle, and vice versa, 90 minus the solar elevation angle will give you the zenith angle. This graph is showing that the geometry works out that at solar noon, the midpoint between sunrise and sunset, the zenith angle is equal to the local latitude minus the solar declination. Here we see this. Your latitude is simply how many degrees off the equator you are, here shown for Boulder at 40 degrees north. Your solar declination is whatever latitude the sun's coming in perpendicular to at solar noon, here shown at 23.5 degrees south, which is minus 23.5 degrees in math here. So using this equation, we can actually figure out what the zenith angle will be at solar noon in Boulder. And the equation is simply your local latitude, again Boulder, it's plus 40 degrees, minus your solar declination at whatever time of year you're looking at. Here we're looking at the winter solstice when the sun's directly overhead at minus 23.5 degrees. So 40 minus 23.5, the absolute value of that is 63.5. That gives you the zenith angle at solar noon during December 22nd in Boulder. So thus, taking 90 minus the zenith angle gives you the solar elevation angle, and you'll find that the sun is only 26.5 degrees off the horizon at its highest point in December 22nd in Boulder. So we could do one more example. What is Boulder's maximum solar elevation angle during the year? We're going to be wanting to look at June 21st, the summer solstice, because that's when the sun's going to be highest in the sky. So the solar declination will be 23.5 degrees north. Using our equation, we get the zenith angle equals your latitude, 40 degrees in Boulder, minus 23.5. Your zenith angle is 16.5, which means your sun angle is 90 minus that at 73.5 degrees. Here's Boulder's sun path for an arbitrary day, August 31st in 2016. They show the sun's track on the summer solstice as a green line, rising in the northeast at 5:30 a.m., coming up, crossing the south, and getting to its highest point, as we just found out, and then setting to the northwest. The winter solstice line is shown as blue, and now the sun actually rises to the southeast, comes up, and only gets to about 26.5 degrees off the horizon before setting back down to the southwest. The orange line is simply showing the sun track during the date here, August 31st. Here's Barrow, Alaska, north of the Arctic Circle, which shows during the summer solstice, June 21st, the sun never goes down below the horizon. Instead, it swings around at all angles, all azimuth angles, starts off in the north, heads around to the south, and back around, and just loops around the horizon over time. Of course, during the winter solstice, the sun never gets off the horizon, but it gets pretty close, so you get some scattered sunlight during the daytime hours. This table considers solar intensity and day length to give you the accumulated or the total daily solar radiation reaching the ground. What's shown here is that the largest numbers are not at the equator, but are near 25 degrees north or south during the summer or winter solstices, respectively. Here's a big number at 25.5 degrees north, and here's the larger numbers at 23.5 degrees south. The reason that these numbers are larger at the equator is because not only does the sun get directly overhead here, but there's a greater number of hours of daylight, approaching 14 hours of daylight here, versus the equator, which never sees more than 12 hours of daylight. Okay, so a regional breakout. The tropics, the sun's close to overhead the whole year. There's about 11 to 13 hours of daylight, depending on how far off the equator you are. And the results there is there's limited changes in temperatures over the year, which means a reduced annual temperature range, and high annual average temps since the sun's always pretty close to directly overhead at solar noon throughout the year. The mid-latitudes feature large shifts in the sun angle and large shifts in the length of days. The result of that is large seasonal shifts in temperature. There's bigger shifts in the northern hemisphere than the southern hemisphere due to being a lot more land, which is easier to heat up and cool down than is ocean. The poles have even larger shifts in solar radiation and larger shifts in day length, but solar is still weak in the summer. It's still coming in an extreme angle. Although this would seem to support large seasonal temperature fluctuations, it's not the case in the poles because much of the summer radiation is weak because of that angle, but also much of the summer radiation doesn't go to sensibly heat the atmosphere at the surface. It's simply melting snow. Question: why would the greatest annual changes in temperature be on upper mid-latitude land surfaces? There's a variety of reasons for this. The first is those large seasonal differences in solar intensity. Second is the seasonal differences in day length, but of course that also defines the polar areas too. Here's large tracts of land and far from ocean, so in the northern hemisphere specifically, these large tracts of land allow for interior positions to be far removed from ocean in what's called continentality. A seasonal snowpack is definitely at play here too, which introduces large seasonal shifts in albedo. Here's looking at the annual range of surface temperature. Specifically, this map is looking at northern hemisphere winter temps minus northern hemisphere summer temperatures, and you can see that the biggest change is over these upper mid-latitude land areas for the reasons just explained. Shifting our focus to what causes daytime heating, simply said, the sun heats the ground by radiation. The ground can heat the overlying air, the first 1 to 3 centimeters of air overlying it, by conduction. That warm air can rise by convection and transfer that heat to the upper atmosphere. That daytime heating by turbulence or thermals is limited to around 1 kilometers about the surface, but there are variations. Maximum temps usually occur during the day, well after the maximum solar input, but around the maximum infrared radiation coming down from the sky and clouds. Here I'm using data locally from our Skywatch lab in CU Boulder to look at this variation. So here we see a pretty common day. It's a clear day. The lower graph is showing a pyranometer irradiance. Simply said, it's measuring the solar radiation coming in at the surface of our lab. Here we're showing March 21st, 2016. The sun came up at around 7 a.m., rose to its highest point at solar noon. Here we are in daylight savings time, so that's about 1 p.m., and that's our maximum solar radiation, and then it goes down. I can see that this is clear because there's no chunks taken out of this by clouds. At the same time, the temperature didn't raise to its highest point until later in the day, almost 6 p.m. for this day. So in no way does it correspond to the maximum solar intensity. There's a thermal lag between when you get your maximum solar intensity and when you get your maximum temperature, especially on clear days. But what it does correspond with well is our pyrgeometer measurements, which are measuring the infrared radiation coming from the sky. Almost all that radiation is coming directly from greenhouse gases on a clear day, so if you get those greenhouse gases nice and warm, according to the Boltzmann law, they'll radiate the most IR radiation to the surface, and that's what's being measured in the lower graph here. And this does correspond pretty well with the maximum surface temperature, which shows when the surface is warmest, and really this is measuring the air in our tower, about 20 feet above the surface. When that air becomes warmest, it emits the most IR radiation to the surface. Question: what other factors might contribute to the time of the daily maximum temperature? There's a bunch of things. The movement of air masses in fronts, the timing of when a warm air mass might come in, it's obviously going to change your time of daily maximum temperature. The amount of water plants for evaporation and transpiration, meaning that some of the energy that comes in, the solar radiation, might just be evaporating water and not changing the air's temperature or the surface temperature at all. Sea breeze effect: anybody who lives along the coast might note that there's a certain time where you might think that you'll get the maximum temperature in the afternoon. Instead, it brings in a cooling breeze from the ocean in a thermal circulation that we'll explore later in this class. Also, soil conductivity is something people don't think about much, but what I mean by soil conductivity is that some of the radiation that comes in that warms the surface, some of that heat can actually conduct to the deeper grounds and doesn't contribute to the raising the air's temperature. So the answer here is all of the above and more. A soil conductivity example might look like this. If two regions are at the same latitude, same distance from the ocean, same elevation, same date, which one will most likely have the highest maximum air temperature? So a wet sandy region, a dry region that's solid rock, a dry sandy region. We could also think about which one might have the higher nighttime temperature. So thinking about heat capacity, which is how much energy it takes some substrate to change its temperature 1 degree Celsius, we can think about heat capacities of the soil and thermal conductivity. It turns out if you add water to a soil, you increase both. You increase the heat capacity, how much energy it takes to raise the temperature of it. You also increase the thermal conductivity, how much energy could be transferred to the deeper soil, which therefore isn't available to heat the air above it. So if you add more water, like case A, you could expect a lot more energy to be used going into the soil, and it takes more energy to change the temperature, so you probably expect a lower maximum air temperature here compared to drier regions. Now between the dry region that's solid rock and the dry sandy region, a solid rock is more conductive, which means that it can transfer some energy to the deeper ground, which the dry sandy region cannot because the loosely packed sand grains are not very thermally conductive. As a result, a dry sandy region with a lot of radiation coming in will heat the very surface of the sand, but it can't conduct it to the deeper layers. Instead, it just ends up heating the atmosphere, which is why deserts have such high daytime temperatures. At night, what happens is that the surface radiates heat to the atmosphere, which cools the surface. The deep ground remains warmer, therefore the heat wants to go from the deep ground back to the surface. It can do so more effectively in conductive soil. The wet sandy region, or the region with solid rock, has a source of heat from the deep ground coming to the surface, helping raise the nighttime temperatures from what they otherwise would be. The dry sandy region does not have this effect because it did not store any heat during the day because it wasn't thermally conductive. Nighttime cooling. The surface emits radiation more efficiently than air, so it cools more quickly at night. This can cause an inversion, a low-level inversion where temperature increases with height. This represents a stable layer, just like the tropopause, that resists vertical motion and therefore can trap pollution in a relatively shallow layer near the surface. How much cooling you get overnight is a function of three things: the length of the night, how much humidity is in the air, including clouds and amounts of condensation and deposition that might occur, but also the wind velocities. Higher winds can help mix warmer air above with colder air near the surface and mix out an inversion from happening. Overall, you get the best cooling overnight with dry air, long nights, and light winds. This animation can show this effect. First thing, we're showing still winds here, so there's not a lot of mixing of the warmer air, shown as a red arrow here, with the cooler air near the surface at night, without winds helping it along. Therefore, we're showing an inversion where temperature is increasing with height very drastically near the surface. As you bump up the wind speed, you increase the amount of mixing. Because the wind's forced to go near zero at the surface, faster aloft, this increases these turbulent eddies, which help mix that warm air in the atmosphere with the colder air near the surface, reducing that temperature inversion, reducing it from happening. Increase the wind even more, you reduce the amount of the inversion that can form, and you increase the mixing between the warm upper air with the cold air overlying the surface. In what ways could having more water vapor, in other words higher humidity, reduce nighttime cooling? What about the effects of clouds? Well, the first thing to consider is water vapor is a strong greenhouse gas. It helps trap radiation near the surface, so more water vapor, less IR to escape, and less cooling overnight. You might expect more clouds with more water vapor. Clouds turn out to be even more effective at trapping IR radiation near the surface, so again, less IR can escape, less cooling overnight. Anytime you have enough vapor to condense as dew on the surface of the grass or deposit as frost, that process actually releases latent heat to the air, adding heat to the overall environment. Water has a particularly high heat capacity, which means it takes a lot of energy to warm it up by 1 degree Celsius. It also is reluctant to cool down overnight as a result as well. Wet ground conducts heat to the surface that was stored beneath during the day. Again, this is effect from conductivity. For an example here, Denver has actually similar maximum temperatures as Atlanta, Georgia in the summer. However, our night times are much more cool because we're drier and we cool much more efficiently during the nighttime. This is a Denver sounding from February in 2015 at 6 a.m., a long cold winter night followed by a crisp morning. What's shown here is the temperature profile on the right, as observed from an instrument package on a weather balloon as it flew through the atmosphere here. It's showing the temperature increasing drastically with height, in other words, a low-level temperature inversion. These inversions, again, resist vertical motion, trapping whatever is in the lower atmosphere to that level. In this case, it can be pollution in the winter where we have our worst pollution episodes because these inversions help trap those pollutants near the surface. There wasn't much winds here, 5 knots from the southeast and then 5 knots from the northwest as you go a little bit higher, which represents pretty weak winds, not able to mix up this temperature inversion. So altogether, the amount of daytime heating you can get and the amount of nighttime cooling go together, you give your total daily or diurnal temperature range. The best case scenario is clear skies, dry air, and calm winds. They're going to give you the biggest range since clear skies is going to allow a lot of solar radiation to come in and get absorbed during the day, and also clear skies is going to allow a lot of outgoing radiation to leave during the night, cooling you back off. Subtropical deserts have the world's largest diurnal temperature ranges for these very reasons. In addition, those subtropical deserts have loosely packed sand, which reduces the soil conductivity, and that is a factor as well. In the equator, the daily range far exceeds the seasonal range, simply because the seasonal range is hardly anything, because the sun's always close to overhead throughout the year. Of course, over the course of a day there, it has a drastic variation where it comes up in the middle of the day and it goes down for 12 hours overnight. The poles have a small daily range in temperature, since the sun's either up all day or down all day. The oceans have a very small diurnal temperature range because they have a very high heat capacity, and we'll look at this quantitatively next lecture. Northern Hemisphere land has a pretty big temperature range, with the largest over dry areas. Again, humidity can reduce the diurnal temperature range. Here's looking at the day-night air temperature range. Dry sandy regions again have the largest diurnal temperature ranges on Earth. We're seeing that in the Sahara, much hotter during the day compared to the night, over the Australian deserts, over the South American deserts, etc. And then you're seeing over the oceans, there's hardly any change from day to night. Again, because it's hard to change the temperature of the oceans with any energy input into them.